Okay, physics students, so this is the second video for chapter 7, momentum and impulse. On the first video I went through sort of the core principles. Now we're going to really expand our investigation of momentum and also impulse. So let's get set up here. We know the drill, we've been through this. Okay. And that looks good. Pretty good. Good enough. It's going to work. Okay. Momentum and impulse. Collisions. Let's talk about collisions. All right. So collisions. Two things collide. How can we describe a change in velocities of colliding football players or balls colliding with bats, right? Like in baseball. How does a strong force applied for a very short time affect the motion, right? That would be impulse. Can we apply Newton's laws to collisions? Well, you bet we can. That's what we're gonna do. That's what we're doing here. That's the whole basis of what we're doing here. What exactly is momentum? Well, yeah, right. Of course, we all sort of know what momentum is. We have a feel for it, but this is physics class. We're gonna define it precisely, right? And conservation of momentum. We'll get into that. Okay, so when you bounce a ball, right? We've all done this. We've all seen it happen. When it reaches the floor, the velocity quickly changes direction, right? Common enough thing. Of course, physics, you can't just leave it at that. We got to study the heck out of things and really examine it. So there must be a strong force exerted on the ball by the floor. Yeah. Bounces right back up. During the short time they are in contact, right? Boop, just hits the floor quickly, pops back up. This force provides the upward acceleration necessary to change the direction of the ball's velocity, right? When I first study physics, I always kind of go, well, the floor didn't hit the ball back, right? It's just sitting there, but no, the floor, the way we're defining it in physics class. Okay, this force provides the upward acceleration. So there must be a strong force exerted on the ball by the floor. Yeah, the floor didn't move, so essentially, right, it's providing that. So that's the way we're defining it, okay? Slightly different than how we would use terminology in our normal discourse, right? Okay, so that's the thing to remember, right? In science, we define things differently, more precisely, so. Forces like this are difficult to analyze. Yeah, they can be, but it doesn't mean we're not going to do it. Just because it's difficult doesn't mean we're not going to do it, right? We're taking on that challenge. Forces that may change rapidly during a collision. All right, so yeah, and this is going to help a lot. So it will help to write Newton's second law in terms of the total changes in velocity over time instead of acceleration. So we already know force equals mass times acceleration. We already know that. So force equals mass, then acceleration is just velocity over time, right? A change in velocity, delta V, a change in velocity over delta T, a change in time, right? That's all acceleration is, right? It's the change in velocity over time. We've been through that. We all know that. So mass times acceleration, force. So now we're going to take that, we're going to take this, so force equals mass times acceleration, so velocity over time is just acceleration. Now, let's just move this delta T over here, right? So do the algebra, multiply both sides by delta T, right? And you'll have force times delta T. It's no longer here because you multiplied it, right? So it canceled out. This is in the denominator. So force times time is equal to mass times the change in velocity. Well, in our previous video, right? Momentum is mass times velocity. Okay? That's our definition of momentum. And our definition of impulse is force times time. Force times the change in time. So interesting. So impulse is equal to momentum, right? Although they have different terms, so they mean different things, but they're equal to each other, right? Impulse can change momentum, right? If you have if you have a bowling ball and you bang it, right, and or if the bowling ball is rolling, so the bowling ball is rolling, it has momentum, and you come by and you push it, right? Well, you've imparted an input. Now you're going to change that momentum. See how it all comes together, right? Okay, so multiply both sides of Newton's second law by the time interval over which the force acts. Okay, well, that's a nice way of saying what I said. The left side of the equation is impulse. Okay, the average force acting on an object multiplied by the time interval over which the force acts. So how a force changes the motion of an object depends on both the size of the force and how long the force acts, right? Yeah, you can bop the bowling ball that's rolling, or you could kind of like really kind of sort of shove it, right? There's different, I'm using popular vernacular, not physics terms, right? To say how you would impact that bowling ball. The right side of the equation is the change in momentum of the object. Okay. Momentum of the object is the mass of the object times its velocity. Mass times velocity is the momentum. Okay? Yeah, and then we're defining momentum as mass times velocity. Be sure you viewed the previous video, right? I went into that in more detail. So, okay. Oh, what happened? Do I want to go back to that one? Let me go back. Maybe I do, maybe I don't. Let's look at that. Okay, a bowling ball and a tennis ball can have the same momentum if the tennis ball with its smaller mass has a much larger velocity. Now you would think, what? Okay, well, say you're laying down on the floor and I take a bowling ball and it rolls at you. It's rolling really slow and it just kind of nudges up against you, right? No harm done. Okay, even though a bowling ball is heavy. A tennis ball is a soft little thing. But if I took that tennis ball and threw it at you as hard as I could, it would hurt, right? You know, if I hit you in the back, it would hurt. So the velocity makes a big difference. The velocity component matters, right? Now, of course, if I had a bowling ball going at a high velocity, well then, yeah, I could crash that through a wall of a house or something, right? So, okay. Okay, impulse momentum principle. The impulse acting on an object produces a change in momentum of the object that is equal in both magnitude and direction to the impulse, right? Vectors, direction matters, yeah. So, and we've already specified this, but this is good. Impulse equals a change in momentum. Okay, delta. Remember this triangle, that's the sign for delta. Change momentum, delta P. Okay, when the ball bounces back with the same speed, the momentum changes from minus, yeah, and this is direction, right? When you're working with vectors and you want to assign a plus to one direction and a minus to another direction. So, okay. Okay, now this is kind of good. So we can all sort of really understand this. Does Newton's third law still hold? Well, Newton's third law always holds. But we'll explain why, right? For every action, there is an equal but opposite reaction, right? The defensive back exerts a force on the fullback, and the fullback exerts an equal but opposite force on the defensive back. Okay, so you have these two football players and they, collide into each other. Okay. If the net external force acting on the system of the objects is zero, the total momentum of the system is conserved. So what we're saying is that we're only talking about these two football players. We're not talking about that they're on Earth and Earth is rotating and Earth is orbiting the sun, right? And no, we're just talking about, okay, we're only going to look at these two football players in isolation. So the net, so the momentum of the system is conserved, right? So this guy has a mass times velocity. This guy over here has a mass times velocity, right? And they're going to collide into each other, and you're going to conserve. Let's get into that so we can really explain what that means. So the impulse on both are equal and opposite. Okay. The changes in magnitude for each are equal and opposite. Yeah, they're bumping into each other. And the total change of momentum for the two players is zero. So what that means is that this player, before he hit this player, he had a momentum, right? This player had a momentum. When they collide, it doesn't just disappear. It affects each other, right? So you now have an impulse. You have a force, and then there's a time when they bump, right? Now the impulse, are they gonna bounce off? Are they gonna hang on? Those things matter, right? So they're gonna feel it, right? And then if one player is bigger than the other, if one player is running faster than the other, it's gonna move the other person. So that momentum is going to affect the system, and you're going to have a net result at the end of that, right? It's gonna add the momentum of each, so it's conserved. You haven't lost it. Something's going to happen with it, right? So here you go. You have 100 kilogram fullback, right? So what's that? That's 240 pounds or something. Roughly, like I'm doing it in my head. Fullback moving straight downfield and collides with a 75 kilogram defensive back, right? So here are these two. So this guy's bigger than this guy, right? The defensive back. But what happens is when he hits him, he doesn't bounce. He hangs on to him. So they become like a unit, right? So it's like, boom. Well, now what happens? So the defensive back hangs on to the fullback, and the two players move together after the collision. What is the initial momentum of each player? All right. So this is a good one. I like this one. This one's fun. So the fullback. So his momentum is mass times velocity. So he weighs 100, or his mass is 100 kilograms, right? Not weight. His mass is 100 kilograms. He's moving at 5 meters per second. So m times v is 500 kilograms, meters per second. No, it says meters per second squared. That's a mistake, isn't it? Momentum is mass times velocity. Okay, folks, look at that. You all found this with me. This PowerPoint, right? Okay, right? This is what you think. You don't just blindly. So that should be kilograms, meters per second. Look at that, whoever did this PowerPoint, all right? But we found it. We're good, right? Good stuff. Good work, folks. Okay, so that's this person. Let's keep going. So this person, mass times velocity. Now they put a minus sign because he's going in the opposite direction, right? So it's vector. So you assign a minus sign to one direction or the other, right? So all the math works out. So it's 300 kilograms in the opposite direction because it's a vector, right? The two arrows are pointing. So it's in the opposite direction for vectors, right? You read that section on vectors in the appendix. And he's going 4 meters per second. So it's kilogram meters. So his momentum is minus 300 kilogram meters per second. Okay? What is the total momentum of the system? Well, yeah, now we just do a little bit of math, so it's not that bad. So the momentum of the fullback plus the defensive back, you have 500, okay, they corrected it now. 500 kilograms meters per second minus 300 kilograms meters per second is 200 kilograms meters per second. You just add it, folks, right? So that's good news, right? We can all do that math. I'm just checking the camera. Hopefully you're getting all this. It looks okay. Okay. So the total momentum adds up, right? Hasn't been lost. It's combined. What is the velocity of the two players immediately after the collision? Well, we have enough information to figure that out. So the total mass is 175 kilograms. The velocity, so you would just take the momentum, which we figured out, which was the total momentum was 200 kilogram meters per second divided by 175 kilograms of total mass, and their net velocity is going to be 1.14 meters per second squared in this direction, because this guy was bigger, right? So this guy hung on to him, but he's gonna, right? It's slower, but they're all going to be going in that direction now, okay? The arrow, that direction. Recoil, let's talk about recoil. Okay, so if you've ever, seen on TV, or if you've, done the target practice, they shoot those clay skeet, right? And they shoot it. Well, a shotgun, it's going to put a lot of recoil on the person's shoulder, right? Why does a shotgun slam against your shoulder when fired? Sometimes painfully. Okay. Now here's another thing. How can a rocket accelerate in empty space when there was nothing there to push against except itself? Some people have a problem with the second one, right? They understand if a rocket blasts off from Earth, it pushes off from the Earth, but if it's up in space, does it work? Well, yeah, it works. It's the propellant is pushing against the rocket and vice versa, right? So, but we'll show that. Okay, so here's they're going to show a problem. So you have two skaters that are on ice, a bigger person and a smaller person, and they're going to push. So this is a good. We can all this. We've all seen this on TV. This is California, but maybe you've ice skated before, roller skated. So two skaters of different masses prepare to push off against one another. Which one will gain the larger velocity? The more massive one? The less massive one? Okay. Well, the answer is B, the less massive one, right? So if we all sort of know that. If they push, well, this small person here is the one who's gonna have more velocity and go backwards, right? Okay, then the next external force acting on the system, the net external force acting on the system is 0. So conservation of momentum applies. So what they're saying is that, they pushed and it's just saying, so this person is going to get the brunt of the momentum, right? Her velocity is going to be higher going this way. This person had a bigger mass, so they're going to go this way a little bit, but it's the same. Her mass times velocity going this way is going to be the same as this person's mass times velocity going this way, but she has more mass, less velocity, less mass, more velocity. It's going to equal. Okay? And we just said that, right? So you have momentum in one direction and then opposite direction, and momentum so they're equal. They're equal. Mass times mass 1 times velocity 1 is equal to mass 2 times velocity 2, right? This person has more mass, it's going to be a smaller velocity. This person has less mass, but it's going to have a larger velocity, but the momentum will be equal on both sides. Okay, recoil is what happens when a brief force between two objects causes the objects to move in opposite directions, right? Recoil. Recoil, something bounces, right? If you're playing pool balls, bounce off each other. Okay? Is momentum conserved when shooting a shotgun?